Hello students, welcome to this lesson 1, chapter 6, application of derivatives. I have already uploaded one lesson on rate of change of quantities. That is only one lesson because the concept is very simple. This lesson, increasing and decreasing function, this is a little bit bigger because the concept here we have to study in detail, and this is also connected with one more concept, that is maxima minima, which is coming under the application of derivatives. Therefore I may have to take one, two or three lessons for this increasing and decreasing function. Let us start. Increasing function and decreasing function. Consider y equal to f of x, say equal to 2x plus 3 in the interval 1 to 5. Let me draw the graph. See, this is the graph of the function. It's a straight line. Now what is special here is when x is 1, y is 5. You can see when x is 2, y is 7. When x is 3, y is 9. When x is 4, y is 11. And when x is 5, y is 13. The speciality which you have to note here is as x increases, y also increases. So such functions are called increasing function. This is the mathematical concept. Therefore I have given a very simple example just to understand what is the meaning of increasing function. Let us take another function, y equal to say f of x, that is equal to minus 2x plus 70 in the same interval 1 to 5. See, when you draw the graph, it will be like this. When x is 1, y is 15. When x is 2, you can see y is 13. When x is 3, y is 11. And when x is 4, y is 9. When x is 5, y is 7. So here what you can observe is, see, when x increases from 1 to 5, y actually decreases. See, when x is 1, it is 15. When x is 5, it is 7. So it is reverse. Therefore this is decreasing function. So these are the two concepts. Sometimes functions increases, sometimes functions decreases. In this chapter, let us study mathematically the meaning of increasing and decreasing function, then definition of increasing and decreasing function, and their nature, etc. Increasing function. Let us take a function y equal to f of x in an open interval AB. Let us take x1 and x2, 2 points. So it is value f of x1 and value is f of x2. At x1 it is f of x1 and x2 f of x2, and the condition is x1 is less than x2. Of course we have taken it in an open interval I equal to AB, and what we observe here is f of x1 is less than or equal to f of x2. Equality is also included because sometimes function may be not increasing, it may be equal, that means flat, but then still it is increasing because it is not decreasing, it is not coming down, so it is increasing. So that is the idea. So we call it as increasing function. So definition is this: let I be an open interval contained in the domain of the function f. Then f is said to be increasing on I if this condition x1 is less than x2 in I implies f of x1 must be less than or equal to f of x2. So this is the definition of increasing function. Of course, for all x1 and x2 belonging to I. So this is the idea. Now there is one more concept, strictly increasing. Let us see what it is. Strictly increasing function. Look at this diagram. The function y equal to f of x is strictly increasing. So it is not flat at any point. So AB is the open interval. You take x1. So it is f of x1, functional value. x2 another point, functional value is f of x2, and condition is x1 is less than x2. Now you can see here, of course, open interval IB we have taken. Now f of x1 is strictly less than f of x2. So in such cases, we call it as strictly increasing function. If equality is there, it is increasing simply. If equality is not there, it is strict increasing function. So definition is same thing, only small change. Let I be an open interval contained in the domain of the function f, then f is said to be strictly increasing on I if x1 less than x2 implies f of x1 is less than f of x2 for all x1 x2 belonging to I. This is the definition. So there are two types of increasing function. One is increasing function, another one is strictly increasing function. Same way we can also define decreasing function. So decreasing function. First, since I have given you in detail the idea of increasing and strictly increasing function, here that much explanation is not necessary. Let me give the definition. Let I be an open interval contained in the domain of real valued function f. Then f is said to be decreasing on I if x1 less than x2 in I implies f of x1 is more than or equal to. It is just inequality reverses for all x1 x2 belonging to I. So this is the graph. See, here you see that flat indicates equality is also possible. So that is the difference. Now decreasing function. Same way, what is the strictly decreasing function? Let I be an open interval contained in the domain of real valued function f. Then f is said to be strictly decreasing function if f of x1 is less than x2 in I implies f of x1 is more than f of x2. x1 less than x2 in I implies f of x1 is more than f of x2. Inequality reverses. So the graph is like this. So here it is strictly decreasing function. So 4 concepts you have to understand: strictly increasing, strictly decreasing and decreasing. Now there is one more possibility. Look at this curve. Sometimes increasing, sometimes decreasing. Therefore this type of function is called neither increasing nor decreasing function. The function increasing at a point. See, this we have to understand. Look at this diagram. F of x is a function in an interval, given interval. See, x1, x2 is the open interval and x0 is a point belonging to that point. Now we say that it is increasing at x0 because this is the reason. F of x1 less than f of x2 less than or equal to f of x0. See, that means if you take any point left of x0, f of x1 is less than or equal to f of x0. Similarly, if you take any point x2 on the right side, any point, so then f of x2 is more than f of x0. Equality is also valid because it is not strictly increasing. This is the idea. Similarly, decreasing function, what you have to understand is, at a point a function is decreasing if you can find an interval x1 x2 such that left of x0 f of x is more, right of x0 f of x is less. Therefore you can say this way: f of x1 is more than or equal to f of x0 and f of x0 is more than or equal to f of x2. So if this is the thing, then at that particular point we say that function is increasing or decreasing. So this is another idea. Then definition: let x0 be a point in the domain of definition of real function f, then f is said to be increasing at x0 if there exists an open interval I such that I equal to x0 minus h, x0 plus h, such that f is increasing in I. See, this is the diagram. Look here, y equal to f of x is the given function and x0 is the point and f of x0 f of x0 is the coordinate of p. Now here in the entire interval function is increasing, meaning b here is x0 minus h. That means you take any small value h, x0 minus h is a point which is left of x0. x0 plus h is a point which is right of x0. So in the entire interval BC, the function is increasing. Therefore, this is the meaning of the function is increasing at. So let x0 be the point in the domain, then said to be increasing in that point. If you are able to find an interval, small interval, where it is increasing. What is that interval? It is x0 minus h, x0 plus h, and it is an open interval. So this is the idea. So that is, there exist x1 and x2 belonging to I such that x1 less than x2 implies f of x1 less than f of x2. So where these two values are belonging to the interval x0 minus h and x0 plus h, and I have taken here in the diagram x0 minus h as b and x0 plus h as c. So this is another definition. Next definition is this: let x0 be a point in the domain of function of real function f, then f is said to be strictly increasing. See, the same thing only. Strictly increasing means equality sign is not there. That is the only difference. You can see here once again x0 is the point and bc is the open interval. What is b? It is x0 minus h. What is c? It is x0 plus h. Now in that interval, whatever value x1 and x2 you take, such that x1 is left of x0, x2 is right of x0, then x1 there exists x1 x2 in I such that x1 less than x2 implies f of x1 is less than f of x2. In such cases we say that the function is increasing at x0, but here it is strictly increasing because strict inequality is there. So this is the thing. Next, same thing, let x0 be a point in the domain of the definition of real function, then f is said to be decreasing at that point x0 if there exists an open interval I equal to x0 minus h, x0 plus h, such that f is decreasing. So this is the diagram. Here also at x0 you draw a vertical, then take one point. For example, you see b means x0 minus h and c means x0 plus h. Then in that interval, whatever value you take, for example x1 and x2, two red lines, vertical red lines, one left, one right I have shown. So the condition is x1, here there exists x1 and x2 such that x1 is less than x2, but f of x1 is more than or equal to f of x2. You can see there in the diagram. And same thing, this is decreasing. Strictly decreasing means instead of equality we have to use only strict inequality. So that is the next definition. So let x0 be a point in the domain of definition of real function f, then f is said to be strictly decreasing at x0 if there exists an open interval I, x0 minus h and x0 plus h diagram. So here x0 is the value and f of x0, that is the point P, and right of x0 c, that means c is x0 plus h, left of x0 that is b, that is x0 minus h. Now this is strictly decreasing means actually there exist x1 and x2, two red lines, one left side of x0, another one right side of x0 I have seen. It is very clear from the diagram. Left side the red vertical line is more, right side the red vertical line is less. So it is very clear x1 less than x2 implies f of x1 strictly more than f of x2. So it is strictly increasing function. Strictly decreasing function at that point. So this is the idea. Now how to determine whether the function is increasing or decreasing? Now this is the next question. One method I have already shown while introducing. Draw the graph, then decide. This is one method, definitely. So one is using definition, using theorem. But we don't want to draw the graph because every time drawing graph is difficult. So we can decide whether the function is increasing or decreasing using the definition and using the theorem. So let us study both of them. Using definition, let me see how we can decide whether a given function is increasing or decreasing using definition. Of course, this has a limited application, but let us just see how it can be done. Let us take, for example, show that f of x equal to 3x plus 2 is increasing for all x belonging to R. That means it is always increasing function. So how to show? Let us take, for example, see what is the definition? F is increasing if, what is the condition? x1 less than x2 implies f of x1 is less than or equal to f of x2. Equality sign if it is simply increasing, inequality if it is strictly increasing. So that is the only difference. Now let us prove like this. Let x1 and x2 be two real numbers in the interval, then such that x1 is less than x2. Whatever may be two real numbers here in the domain. Now 3x1 is definitely less than 3x2. When you multiply by a positive real quantity, inequality remains same. So this implies now, if you add, last year you have studied linear inequality, if you add 2 to both sides, still inequality is valid. So this implies, what is 3x1 plus 2? It is f of x1. What is 3x2 plus 2? It is f of x2. Now look here, x1 less than x2 implies f of x1 less than f of x2. So this implies f of x is increasing function. So this is the way we can prove it. And here one more thing is, it is strictly increasing function because strict inequality is there. Next example, show that f of x equal to minus 2x plus 5 is decreasing for all x belonging to R. See solution. What is the definition of decreasing? F is decreasing if x1 less than x2 implies f of x1 is more than or equal to f of x2. Therefore, you have to prove using this method only. Suppose x1 and x2 be two real numbers such that x1 is less than x2. Then when you multiply by minus 2, inequality changes. Last year you have seen this one. Then add 5, inequality will be same, adding. So minus 2x1 plus 5 is more than minus 2x2 plus 5. But what is minus 2x1 plus 5? That is f of x1 is more than f of x2. Now look here, whenever x1 is less than x2, if f of x1 is more than f of x2, the function is increasing. Definition. So by definition, f of x is decreasing. So this is strictly decreasing actually, because strict inequality is there. So it is decreasing. So thus, using the definition, we can prove the given function increasing or decreasing, but it is not easy. So I have taken only very simple example where it is easy, but using definition you cannot prove inequality, increasing and decreasing function for all given function. There are difficulties, but for simple questions we can do it. Now theorem. So there is a theorem which will help us to decide whether the function is increasing or decreasing. That is very interesting. Let f be a continuous at closed interval AB and differentiable in the open interval AB. Then first one, f is increasing in AB, that is closed interval, if f dash x is positive for all values x belonging to AB in the entire interval, not only at that one particular point, the entire interval it is increasing, provided f dash x must be strictly positive. So this is one thing. Second one is f is decreasing in closed interval AB if f dash x is negative for each x belonging to AB in the entire interval. And there is one more condition, f is constant in the interval AB if f dash x is 0 for each x belonging to AB. These are the three important conditions, and this theorem will help us to decide whether the given function is increasing or decreasing without even drawing the graph. Let me just explain with the help of a diagram. Look at the first one, f is increasing in AB if f dash x is positive. This is the idea. See, the given function is in the closed interval AB, f dash x is positive. So it is increasing. It is increasing means f dash x is positive. This is the idea. Similarly, for the decreasing function, you see, for the decreasing function, you can see here there is a red graph, so which is decreasing, and for the entire interval AB, f dash x is negative. So this is the idea. Third one is when in the entire interval AB, if f dash x is 0, that means the function is constant. So it is horizontal or parallel to x-axis. Slope is 0, so parallel to x-axis. That means function is not increasing, not decreasing. It is constant. So this is the three important conditions for increasing, decreasing and constant function. Now let us proceed. Let us try to prove this one. let f be a continuous at AB and differentiable in AB. Suppose f dash x is positive in I, then we can show that it is increasing. Let x1 and x2 belonging to AB such that x1 is less than x2. Then by mean value theorem, there exists a value C between x1 and x2 such that, see, this we have studied in the fifth chapter, f of x2 minus f of x1 divided by x2 minus x1 will be equal to f dash C, and this is mean value theorem. So now f of x2 minus f of x1 equal to, therefore, x2 minus x1 into f dash C. Now see here, this is positive. Why it is positive? You see, x1 is less than x2. Therefore, x2 minus x1 is positive. Now second one is, suppose f dash x is positive in the entire interval, it is also positive for f dash C. Therefore, this is positive. So this implies f of x2 minus f of x1 is positive. This implies what? F of x2 is more than f of x1. This implies f of x1 is less than f of x2. So by definition, now look at the condition, x1 is less than x2 implies now f of x1 is less than f of x2. Definitely the function is increasing function. So by definition, so f is increasing in I. So this is the proof for increasing. Exactly same way we can also show that if f dash x is negative, then function is decreasing. Second case, suppose f dash x is negative in I, then let us take x1 and x2 belonging to closed interval AB such that x1 is less than x2. Now then by mean value theorem, there exists a value C between x1 and x2 such that f of x2 minus f of x1 divided by x2 minus x1 will be equal to f dash. This we have studied in the chapter 5. Now once again, f dash x2 minus f dash x1 equal to x2 minus x1 into f dash C. But here now x2 is more, x1 is less, so x2 minus x1 is positive. But what about f dash C? It is negative because condition is f dash x is negative, so f dash C also must be negative. So this is the reason, x2 minus x1 is positive but f dash C is negative. Therefore f of x2 minus f of x1 is negative. This implies f of x2 is less than f of x1, or we can also write it as f of x1 is more than f of x2. So now look here, x1 is less than x2 but f of x1 is more than f of x2, reverse. So this by definition f is decreasing. This is the proof for the second part. Now let us proceed. Third one, suppose f dash x is 0 for all values in I, then what happens? Let us take x1 and x2 belonging to AB such that x1 is less than x2. Now by mean value theorem, there exists a point C between x1 and x2 such that, this is the condition, f of x2 minus f of x1 divided by x2 minus x1 equal to f dash C. But now this will be equal to x2 minus x1 into f dash C. But condition is f dash x is 0 for all values, means it should be 0 for f dash C also. So this is 0 because f dash C is 0. Therefore f of x2 minus f of x1 equal to 0. This implies f of x2 equal to f of x1. And note here, x1 and x2 are any 2 points. That means this implies f of x1 equal to f of x2, or f is a constant, because for any 2 points f of x1 equal to f of x2 means f must be a constant function. So this is the proof for the third part. Now let us take a few illustrative examples to understand the significance of this theorem. But remember this much, for increasing f dash x is positive, for decreasing f dash x is negative. So example 1, show that f of x equal to 2x plus 3 is strictly increasing function. So now you need not use the definition. We have f of x equal to 2x plus 3. Therefore f dash x equal to 2. It is strictly positive. So by theorem, f of x is strictly increasing function. Second example. Show that the function f of x equal to minus x plus 3 is strictly decreasing function. So solution is, we have f of x equal to minus x plus 3. So f dash x is negative. This implies f of x is strictly decreasing because f dash x is negative. Theorem. So this is the next example. Show that f of x equal to x square is increasing function, very important, in the interval 2 to 3. In the interval 2 to 3. Now we have f of x equal to x square, therefore f dash x equal to 2x. But now 2x is positive because the given interval is 2 to 3. So in 2, 3, therefore by definition it is increasing function. So it is strictly increasing because it is not even 0. So this is the third example. Next example, example 4. Show that the function f of x equal to x cube minus 3x square plus 4x is strictly increasing in R. That means we have to show that f dash x is strictly positive. So we have f of x equal to x cube minus 3x square plus 4x for all x belonging to R. Let us find f dash x. So it is 3x square minus 6x plus 4 after differentiation. So now look here, we can do like this. Take 3 common, 3x square minus 2x plus 3. 4 I have split into 3 and 1. So that it is 3x square minus 2x plus 3 plus 1 is 4. I have not changed anything. I have just rearranged. Now this we can write 3 into x minus 1 whole square plus 1. Whatever may be the value of x. X minus 1 whole square is always a non-negative quantity. 3 into a non-negative quantity is always non-negative. Plus 1 is always positive. So this is always positive. Therefore f is strictly increasing function. So this is how we can prove. So thank you for watching this lesson. Please subscribe if you have not yet subscribed and share with your friends. Let us meet in the next lesson. As I told you, this lesson is of course a little bit difficult because the concept of increasing in an interval, increasing at a point, etc. we have to be very careful. Please revise, and very important thing is the theorem. One single theorem will help us to decide whether the function is increasing or decreasing at a particular point. So please revise, and in the next class let us take the examples from the exercise increasing and decreasing function. Let us meet in the next lesson with examples. Till then, bye, take care.